Welcome to Dreamy Science, where we explore the fascinating world of scientific wonder. Here's something that should truly twist your brain into knots. Imagine a star far larger than our Sun that has lived out its fiery life. It's exhausted its nuclear fuel, and the immense outward pressure that once counteracted its own gravity has vanished. This star begins to collapse, shrinking under its own colossal weight. Now picture it shrinking not just to the size of a planet, but to the size of a city, then a house, then a marble, and then, impossibly, to a point so incredibly tiny, so infinitesimally small that it has no discernible volume at all. It becomes a singularity, a point of infinite density. All the mass of that enormous star compressed into a space smaller than a single atom. And around this point, gravity becomes so ferocious, so utterly overwhelming that nothing, not even light itself, can escape its grasp. This isn't science fiction. This is a black hole. It's not a hole in space, but rather a region where space and time itself have been so profoundly warped, so violently curved, that they simply fold in on themselves. We're talking about objects where the very fabric of reality, the stage upon which the universe plays out, is torn and twisted into an extreme, inescapable vortex. The implications of these cosmic monsters are so profound, so challenging to our everyday intuition, that they force us to confront the very limits of physics and the ultimate nature of existence. They are not just vacuum cleaners of the cosmos, they are cosmic laboratories, where the laws of physics are pushed to their breaking point, revealing the deepest, most unsettling truths about our universe. They are, quite literally, where the universe starts to break. If you're enjoying this journey through the fascinating world of science, I'd love it if you'd hit that like button and subscribe to Dreamy Science so you don't miss future episodes. And I'm always curious. Drop a comment letting me know what city you're watching from and what time it is where you are. There's something special about knowing this exploration of scientific wonder is reaching people all over the world at all hours of the day and night. Chapter 1. The Ultimate Cosmic Paradox: How Black Holes Represent the Most Extreme and Counterintuitive Objects in the Universe, Challenging Our Fundamental Understanding of Reality. Let's begin with a thought experiment that sounds utterly impossible. Imagine you're standing on the surface of a celestial body. You throw a ball straight up into the air. On Earth, it goes up, slows down, and comes back down. If you throw it harder, it goes higher. If you throw it hard enough, about 11.2 kilometers per second, or 25,000 miles per hour, it will escape Earth's gravity entirely and never come back down. That's Earth's escape velocity. Now, picture a place where the escape velocity isn't just faster than a rocket, but faster than light itself. That's the mind-bending reality of a black hole, a place where the very speed limit of the universe isn't fast enough to get out. At its core, a black hole is a region of space-time where gravity is so incredibly strong that nothing, not even particles travelling at the speed of light, can escape from it. This isn't because there's a physical barrier, but because the fabric of space-time itself has been warped and pulled so tightly around a central point that all paths, including those of light, lead inwards. It's like being on a river where the current is faster than your boat can possibly go upstream. No matter how hard you row, you'll always be pulled downstream. In the case of a black hole, downstream means towards the singularity, and upstream means out into the wider universe. This extreme gravity arises from the incredible compression of matter. Take, for instance, our own Sun. If you could somehow squeeze all of its immense mass, which is about 330,000 times the mass of Earth, into a sphere just 6 kilometers, about 3.7 miles across, it would become a black hole. Its density would be unimaginable. A single teaspoon of material from such an object would weigh billions of tons. But the sun won't become a black hole, it's not massive enough. Black holes typically form from stars that are at least 20 to 30 times more massive than our sun. When these colossal stars exhaust their nuclear fuel, the outward pressure generated by fusion reactions can no longer counteract the inward pull of gravity. The star collapses catastrophically under its own weight, crushing its core into an infinitely dense point called a singularity. The boundary around this singularity, the point of no return beyond which nothing can escape, is called the event horizon. It's not a physical surface you could stand on, or even a tangible membrane. Instead, it's a theoretical boundary, a sphere in space where the escape velocity precisely equals the speed of light. Once you cross this invisible line, you are committed. There is no going back, no matter what you do. Even if you could instantaneously accelerate to the speed of light, you would find yourself moving inexorably towards the center of the black hole. This is perhaps the most unsettling aspect. The event horizon isn't just a barrier in space, but a boundary in time. All future paths for anything that crosses it lead to the singularity. The idea of such an object first emerged from Albert Einstein's theory of general relativity, published in 1915. Einstein's revolutionary idea was that gravity isn't a force pulling objects together across empty space, but rather a manifestation of the curvature of space-time caused by mass and energy. Massive objects like stars and planets create dips or wells in the fabric of space-time, and other objects simply follow the curves of these wells. Think of a bowling ball placed on a stretched rubber sheet. It creates a depression, and marbles rolled nearby will curve towards it. A black hole, then, is an object so massive, so dense, that it creates an infinitely deep well, a tear in the rubber sheet that swallows everything. The first person to mathematically describe the properties of a black hole, specifically the radius of its event horizon, was Karl Schwarzschild, just months after Einstein published his theory. He calculated what's now known as the Schwarzschild radius, which is the critical radius to which any object must be compressed to become a black hole. For the Earth, for example, its Schwarzschild radius is tiny, about 9 millimeters, or roughly the size of a large marble. To turn Earth into a black hole, you'd have to squeeze all its mass into that minuscule volume. The fact that the universe contains objects that actually achieve this level of compression is one of its most astonishing features. What does it mean then for the universe to contain such extreme objects? It means that our understanding of space, time, and matter is constantly being challenged. Black holes are not just cosmic oddities, they are fundamental laboratories of physics. They are places where general relativity makes its most extreme predictions, and where those predictions clash most violently with another pillar of modern physics, quantum mechanics. This clash, this fundamental disagreement between our two most successful theories of reality, is what truly makes black holes break the universe, and it's a journey we're just beginning to explore. So, we've established the basic, terrifying reality of black holes. Regions of space-time where gravity is so intense that nothing escapes, formed from the collapse of massive stars and defined by an event horizon that marks the ultimate point of no return. But what happens if you actually fall into one? What does it feel like? What happens to your body, to time, to information itself? And how do we even know these things exist if we can't see them? These questions naturally lead us to the strange and unsettling phenomena that occur in the immediate vicinity of a black hole, and beyond its event horizon, which we will delve into in our next chapter. Welcome back, cosmic explorers, to Dreamy Science. Last time we peered into the heart of darkness, unraveling the birth of black holes and the mind-bending concept of the event horizon. We left you hanging, teetering on the edge of the unknown, with profound questions about what truly happens when you cross that ultimate boundary. What becomes of a person, of time itself, and of the very information that makes up everything we know? And how, in the vast star-studded canvas of the cosmos, do we even find these invisible monsters? Today, we're diving headfirst into those mysteries, venturing beyond the point of no return to confront the most extreme laboratories the universe has to offer. Prepare yourselves, because the answers we're about to explore don't just challenge our intuition, they fundamentally break our understanding of reality. Let's start with that terrifying yet utterly captivating thought experiment. What if you were falling into a black hole? Imagine for a moment that you're an intrepid astronaut, bravely or perhaps foolishly venturing too close. As you approach, you wouldn't initially feel anything unusual, but as you get closer and closer, gravity, already a powerful force, would begin to intensify with a ferocity that's almost impossible to comprehend. This isn't just gravity pulling you down, it's gravity pulling differently on different parts of your body. Think about it. Your feet, being closer to the black hole singularity than your head, would experience a significantly stronger gravitational pull. This differential force is called a tidal force, and near a black hole, it becomes utterly overwhelming. If you were falling feet first, your feet would be pulled much harder than your head, and your body would be stretched out like a piece of cosmic taffy. This gruesome yet scientifically fascinating process has a rather vivid name: spaghettification. Yes, you heard that right. Before you even reach the event horizon of a stellar mass black hole, those immense tidal forces would literally stretch you into a long, thin strand of atoms, like spaghetti. The force would be so extreme that your bones, muscles, and even the very atoms of your body would be pulled apart, elongated along the direction of the black hole and compressed from the sides. It's a violent, inescapable transformation, a testament to the sheer, unbridled power of a black hole's gravity. Now, what if you were falling into a supermassive black hole, like the one at the center of our own Milky Way Sagittarius A? These colossal beasts, millions or even billions of times the mass of our Sun, have event horizons so vast that the tidal forces at the boundary are actually much weaker. You might theoretically cross the event horizon without even noticing it, without being spaghettified, till much, much later. Closer to the singularity itself. A truly chilling thought, isn't it? One moment, you're in the universe as you know it. The next, you've crossed an invisible line from which there is absolutely no return. This brings us to the profound implications for time. Imagine you're the astronaut falling in, and your friend is observing from a safe distance in orbit. From your perspective, as you cross the event horizon, nothing feels particularly special. Time continues to flow normally for you. You might wave goodbye, send a final message, but for your friend watching from afar, something truly bizarre happens. As you approach the event horizon, you would appear to slow down, your movements becoming increasingly sluggish. Your voice, if you were still able to transmit, would drop in pitch and become stretched out. And then, just as you seem to reach the event horizon, you would appear to freeze. Your image would redden, dim, and eventually fade away, seemingly suspended forever at the boundary. This is gravitational time dilation, in action, a cornerstone of Einstein's general relativity. The closer you are to a massive object, the slower time passes relative to an observer further away. At the event horizon, time for the infalling object effectively stops from the perspective of an outside observer. For them, you never truly cross. You are eternally frozen, a ghostly spectre on the edge of oblivion. But for you, the infalling astronaut, time marches on. You experience the finite journey to the singularity, a journey that, depending on the black hole's size, could be agonizingly short or even, in the case of supermassive black holes, last for hours or days from your personal frame of reference. This is one of the most profound ways black holes break our intuitive understanding of time. It's not absolute, it's relative, bending and stretching in the presence of extreme gravity. But the real cosmic conundrum, the one that keeps physicists up at night, revolves around information. In quantum mechanics, a fundamental principle states that information can never truly be destroyed. It might be scrambled, hidden, or transformed, but it's always conserved. Think of it like burning a book. The information contained in the words isn't gone, it's just encoded in the soak, ash and heat, theoretically reconstructible if you had enough data and computing power. Now, consider a black hole. Anything that falls in, a star, a planet, an astronaut, a book, seems to be swallowed completely, its information disappearing behind the event horizon. From the outside, all that's left are three simple properties: mass, charge, and angular momentum. What happened to all the intricate details, the unique quantum information that made up that star, planet, or person? For decades, this was a seemingly impenetrable mystery. Then, in the 1970s, the brilliant physicist Stephen Hawking proposed something utterly revolutionary. Black holes aren't entirely black. They slowly, incredibly slowly, radiate energy, a phenomenon now known as Hawking radiation. This radiation arises from quantum fluctuations near the event horizon, where particle-antiparticle pairs are constantly popping into existence. Sometimes one particle falls into the black hole while its partner escapes, carrying a tiny bit of energy away from the black hole. Over an unimaginably long time, black holes can actually evaporate. A stellar mass black hole would take far, far longer than the current age of the universe to evaporate, but eventually it would disappear. And here lies the crux of the information paradox. If a black hole eventually evaporates and all that's left is Hawking radiation, which seems to carry no information about what fell in, then what happens to the original information? If it's truly gone, truly destroyed, then quantum mechanics is fundamentally wrong. But if it's not destroyed, where does it go? Does it somehow escape with the Hawking radiation, encoded in a way we don't yet understand, or is it preserved in some exotic, higher dimensional realm? This is a direct head-on collision between two of our most successful theories of physics: general relativity, which suggests information is lost inside a black hole, and quantum mechanics, which insists it must be conserved. It's a deep, unsettling challenge that breaks our universe by showing us that our current understanding of reality is incomplete, perhaps even fundamentally flawed at the extreme edges of existence. So we've explored the terrifying fate of an infalling object and the mind-bending implications for time and information. But how do we even know these invisible cosmic behemoths exist? How do we detect something that by definition doesn't let light escape? The answer, as with many things in astronomy, lies in observation and deduction. We can't see black holes directly, but we can certainly see their gravitational influence. Imagine a cosmic dance partner that's completely invisible but incredibly massive. Its partner star would be orbiting around nothing seemingly, but its movements would betray the presence of an unseen gravitational monster. This is one of our primary methods, observing the peculiar orbits of stars or gas clouds around a dark, incredibly dense center. For instance, at the very heart of our Milky Way galaxy, stars are whipping around an unseen object at incredible speeds. Calculations show that this object must be millions of times the mass of our Sun, confined to a region smaller than our solar system. There's only one explanation: a supermassive black hole. Another crucial clue comes from what accretion disks. When a black hole is actively feeding, it draws in gas and dust from nearby stars or clouds. This material doesn't fall straight in. Instead, it spirals inward, forming a flat, swirling disk around the black hole, much like water going down a drain. As this gas spirals closer, it gets superheated by friction and gravitational compression, reaching temperatures of millions of degrees. At these extreme temperatures, the gas emits intense radiation, particularly in the X-ray and gamma-ray parts of the spectrum. We can detect these powerful X-ray flares and jets from across the cosmos, acting as luminous beacons that betray the presence of a hidden black hole. These disks are some of the brightest objects in the universe, a fiery testament to the black hole's insatiable appetite. And then there's the revolutionary detection method that has opened an entirely new window into the universe: gravitational waves. Remember how Einstein's general relativity describes gravity as the curvature of space-time? Well, when massive objects accelerate, they create ripples in this space-time fabric, like pebbles dropped into a pond. These ripples propagate outward at the speed of light, carrying energy away. For a long time, these gravitational waves were purely theoretical, incredibly difficult to detect. But in 2015, the LIGO, Laser Interferometer Gravitational Wave Observatory, experiment made history. They detected gravitational waves emanating from the collision of two black holes, each about 30 times the mass of our Sun, merging into a single, even more massive black hole over 1 billion light-years away. It was an astonishing confirmation of Einstein's theory, and provided the first direct evidence of black holes. These events are incredibly violent, releasing more energy in a fraction of a second than all the stars in the observable universe combined, momentarily warping the very fabric of space-time around us. Detecting these ripples allows us to hear the universe in a way we never could before, picking up the cosmic drumbeat of merging black holes, neutron stars and other cataclysmic events. It's a profound leap in our ability to observe the universe, letting us witness the most extreme phenomena directly. So while black holes remain invisible to our eyes, their presence is undeniable. We see their gravitational pull on other stars, their fiery feeding frenzies, and even the ripples they send through the very fabric of space-time. Each detection, each observation reinforces their reality and simultaneously deepens their mystery. Black holes are not just cosmic oddities, they are ultimate cosmic laboratories, pushing the boundaries of our understanding to their absolute breaking point. They force us to confront the limits of our most cherished theories, from the nature of time and information to the fundamental laws governing the universe. They demand that we rethink, reevaluate, and perhaps, eventually, discover an even deeper, more profound truth about how reality truly works. If you're finding this journey into the extreme fascinating, please hit that like button and consider subscribing to Dreamy Science. Your support helps us continue exploring these incredible frontiers. Next time we'll delve even deeper, asking if there are different types of black holes, exploring the mind-bending concept of wormholes, and considering whether these cosmic paradoxes might hold the key to understanding the very beginning or even the end of our universe. The rabbit hole, my friends, goes even deeper. Welcome back, dreamy science explorers. In our last cosmic journey, we peered into the heart of black holes, witnessing their profound gravitational dance and their stunning ability to warp space-time. We saw how these cosmic monsters act as ultimate laboratories, pushing the very limits of physics and forcing us to reevaluate our understanding of reality itself. We confirm their existence through the telltale wobbles of orbiting stars, the searing glow of accretion disks, and the seismic ripples of gravitational waves. But here's the thing, when we talk about black holes, we're often lumping together a whole family of incredibly diverse cosmic objects. It's like talking about animals when you mean everything from a microscopic tardigrade to a colossal blue whale. Today we're diving deeper into the astonishing variety of these cosmic enigmas, exploring the different flavors of black holes that populate our universe. Each type, with its unique origin and characteristics, doesn't just expand our cosmic catalogue, it opens up entirely new avenues of inquiry, challenging our most cherished theories and revealing just how much more there is to learn about the fabric of existence. We've already delved into the two most famous members of this enigmatic family, the stellar mass black holes and the supermassive black holes. Let's briefly revisit these cosmic heavyweights, shall we? Stellar mass black holes. These are the most common type we know of, born from the spectacular violent death of a truly gigantic star. Imagine a star at least 20 to 30 times more massive than our Sun, burning through its nuclear fuel with ferocious intensity. When it finally runs out of hydrogen, then helium, then heavier elements, the delicate balance between outward radiation pressure and inward gravitational pull collapses. The star implodes, detonating in a supernova explosion so brilliant it can outshine an entire galaxy for a brief moment. What's left behind, if the core is massive enough, isn't a neutron star, but something far more extreme, a stellar mass black hole. These cosmic devourers typically weigh in at a few to several tens of solar masses, and they dot our galaxy, silent, invisible monuments to stellar demise. They are the cosmic debris left over from the grandest fireworks display the universe can offer. We detect them by the way they tug on companion stars, or the way they greedily feast on gas torn from a binary partner, creating those scorching hot accretion disks that scream in X-rays. They are the bread and butter of black hole astronomy, familiar yet still utterly mind-boggling. Black holes. Then we have the undisputed titans, the gravitational behemoths that dwarf their stellar cousins. These are the supermassive black holes, weighing millions, even billions, of times the mass of our Sun. They reside not just in galaxies, but at the very heart of almost every massive galaxy we've observed, including our own Milky Way, which hosts Sagittarius A, a 4 million solar mass monster. How do these colossal beasts form? That's still a question that keeps astrophysicists up at night. Do they grow from smaller black holes through countless mergers and accretion events, relentlessly gorging on gas and stars over billions of years? Or did some of them form directly from the collapse of massive gas clouds in the early universe, skipping the stellar death phase entirely? These direct collapse black holes, if they exist, would be born big, already weighing thousands or tens of thousands of solar masses shortly after the Big Bang. Supermassive black holes are not just passive residents, they are active architects of galactic evolution. They're powerful jets of plasma influencing star formation across vast cosmic distances. They are the ultimate cosmic puppeteers, their gravitational strings pulling the entire galactic stage. But what if there's a missing link? A cosmic middle child too big to be stellar, yet too small to be supermassive. Intermediate mass black holes are IMBHs, the elusive middle child. This brings us to one of the most intriguing mysteries in black hole astrophysics, the intermediate mass black holes, or IMBHs. As their name suggests, these theoretical entities bridge the vast gap between stellar mass black holes, tens of solar masses, and supermassive ones, millions to billions of solar masses. We're talking about objects ranging from 100 to 100,000 times the mass of our Sun. Why are they so elusive? Because they don't leave the same clear gravitational fingerprints as their more extreme relatives. They are not massive enough to dominate an entire galaxy's centre, nor are they as common or as easily detectable as stellar mass black holes in binary systems. Finding an IMBH is like trying to spot a particularly large fish in an ocean teeming with smaller fish and whales. It's there, but it's hard to isolate. Yet the existence of IMBHs is crucial. They are the missing link in our understanding of how supermassive black holes grow. If supermassive black holes truly grow from smaller seeds, then IMBHs are likely those very seeds, or the results of those seeds merging and growing. Imagine a cosmic nursery where stellar mass black holes coalesce, merging repeatedly to form progressively larger and larger black holes. This hierarchical merger scenario suggests IMBHs should be abundant in dense stellar environments, like globular clusters, ancient, tightly packed spheres of hundreds of thousands of stars. Within these clusters, stars are so close together that collisions and subsequent black hole mergers become much more probable. How do we hunt for these cosmic ghosts? We look for subtle clues. Perhaps an IMBH is lurking in the centre of a globular cluster, subtly influencing the orbits of surrounding stars, or maybe, just maybe, we might catch the fleeting gravitational waves from two IMBHs spiralling into each other, a cosmic crescendo that LIGO and Virgo are constantly listening for. Another telltale sign could be a tidal disruption event, where a star wanders too close to an IMBH and is ripped apart, creating a flare of X-rays and ultraviolet light as its matter is devoured. These are the subtle whispers in the cosmic background that hint at the presence of these enigmatic middle children. Their discovery would be a monumental step, not just confirming their existence, but also illuminating the pathways of black hole growth and the evolution of galaxies themselves. But what if we journey even further back in time, to the very dawn of creation, to a time before stars even existed? Primordial black holes, PBHs, relics of the early universe. Imagine a universe so young, so dense, so utterly chaotic that tiny ripples in its fabric could collapse directly into black holes. These are the theoretical primordial black holes, or PBHs. Unlike their stellar mass cousins, PBHs wouldn't form from the death of stars. Instead, they would have emerged in the first moments after the Big Bang, when the universe was an incredibly hot, dense soup of energy and particles. In this infant universe, slight density fluctuations, tiny regions that were just a little bit denser than their surroundings, could have had enough gravitational pull to overcome the universe's rapid expansion and collapse into black holes. Depending on the exact conditions of the early universe, these primordial black holes could theoretically span an incredible range of masses, from minuscule asteroid-sized objects to those rivaling supermassive black holes. Some theories even suggest they could be as light as a mountain or even a single atom. Why are PBHs so fascinating? Because they offer solutions to some of the most profound mysteries in cosmology. One of the most compelling ideas is that PBHs could be a significant component, or even the entirety, of dark matter. We know dark matter exists because of its gravitational effects on galaxies and galaxy clusters, but we have yet to directly detect it. If PBHs exist in sufficient numbers and with the right mass range, they could provide the invisible gravitational scaffolding that holds the cosmos together, without interacting with light or other matter in any other way. This would be a game changer, fundamentally altering our understanding of the universe's composition. Furthermore, PBHs could have played a crucial role in seeding the supermassive black holes we see at galactic centers today, providing the initial seeds around which galaxies could form and grow. They might even explain the origin of some neutron stars or other compact objects. Detecting PBHs is, as you can imagine, incredibly challenging. Smaller PBHs, those less massive than a mountain, would have already evaporated by now through Hawking radiation, that faint theoretical glow that black holes are supposed to emit. But what about the larger ones? If they don't accrete matter, they would be truly invisible, their presence only betrayed by their gravitational influence. We're looking for subtle gravitational lensing events, where a PBH passes in front of a distant star, briefly magnifying its light. We're also searching for unique gravitational wave signals that might arise from their mergers. The hunt for primordial black holes is a journey into the deepest past of our universe, a quest to understand its very origins and its fundamental constituents. Each new type of black hole we discover, or even theorize, doesn't just add another entry to our cosmic catalogue. It throws a wrench into our existing models, forcing us to rethink the very processes that shape the universe and the fundamental laws that govern it. The existence of IMBHs challenges our understanding of black hole growth and galactic evolution. The potential reality of PBHs could rewrite the story of dark matter and the early universe itself. These are not just exotic curiosities, they are cosmic paradoxes that push the boundaries of what we thought possible. They force us to confront the limits of our current theories, particularly the ongoing tension between Einstein's general relativity and quantum mechanics. How can black holes exist in such diverse forms? And what does that tell us about the ultimate nature of space-time, gravity, and the matter itself? From the stellar remnants of dying stars to the ancient whispers of the early universe, black holes are far more diverse and far more influential than we ever imagined. They are not just cosmic destroyers, but potential architects, dark matter candidates, and crucial pieces in the grand puzzle of the cosmos. And as we continue to unravel their mysteries, we find ourselves peering ever closer to the ultimate questions. What lies beyond the event horizon? Could these cosmic devourers also be cosmic architects? And what if, just what if, some of them are not just cosmic destroyers, but gateways to other dimensions, or even other universes? Join us next time on Dreamy Science as we venture beyond the event horizon and explore the mind-bending possibilities of wormholes and the tantalizing prospect that black holes might be more than just cosmic prisons. Perhaps they're cosmic shortcuts, or even the ultimate destroyers and creators of everything we know. Don't forget to hit that like button and subscribe to Dreamy Science if you're enjoying this journey into the extreme, the mysterious, and the profoundly beautiful universe we inhabit. Your curiosity fuels our exploration. Welcome back to Dreamy Science, where our journey into the heart of cosmic mystery continues. We've traversed the vast spectrum of black holes, from the stellar mass remnants of colossal stars to the supermassive behemoths anchoring galaxies. and even speculated on the elusive intermediate and primordial varieties. Each type, in its own way, is a testament to the universe's boundless capacity for the extreme. But regardless of their size, their origin, or their specific cosmic role, all black holes share a fundamental unsettling truth. They don't just exist in the universe. They challenge, twist, and in many profound ways, break our understanding of it. Think about it. We've established that black holes are regions of space-time where gravity is so overwhelmingly powerful that nothing, not even light, can escape. But what does that truly mean for the fabric of reality? It means that at their core lies a concept so utterly alien, so profoundly challenging to our intuition, that it forces us to confront the very limits of our physics. At the very heart of every black hole, general relativity predicts a point of infinite density, an infinitesimally small volume containing all the mass of the collapsed star or coalesced matter, the pure singularity. But what is a singularity? It's not just a tiny dot in space. It's where our current understanding of physics breaks down completely. It's where our most cherished equations, those beautiful mathematical descriptions of the universe, simply throw up their hands and declare, "We don't know." Imagine trying to describe something with infinite density. The very concept is mind-bending. It tells us that general relativity, while incredibly successful at describing gravity on large scales, is incomplete. It's like having a magnificent map of the world only to find a gaping, uncharted chasm right in the middle labelled, "Here be dragons." The singularity isn't just a physical point, it's a profound conceptual tear in the universe's rulebook. This brings us back to one of the most intriguing and frustrating paradoxes we touched upon, the information paradox. If you recall, this is the cosmic tug-of-war between two of our most fundamental theories, general relativity, which suggests that anything falling into a black hole is lost forever, and quantum mechanics, which insists that information can never truly be destroyed. Stephen Hawking's brilliant yet equally perplexing theory of Hawking radiation suggests that black holes slowly evaporate over cosmic timescales, emitting particles. But if these particles carry no information about what fell into the black hole, say the specific quantum state of a book, a star, or even a hapless astronaut, then where does that information go? Does it simply vanish, erased from existence? If information is indeed lost, it would violate a foundational principle of quantum mechanics, a principle that underpins our very concept of a predictable, ordered universe. It would imply that the past might not uniquely determine the future, a truly unsettling thought. Scientists have proposed numerous ingenious, if highly theoretical, solutions to this paradox. Some suggest that the information isn't truly lost, but is encoded in a scrambled holographic form on the event horizon itself, like a cosmic hard drive. Others propose fuzzballs, theoretical objects, where the singularity is replaced by a quantum mechanical fuzz that retains the information. These radical ideas are not just academic exercises, they are attempts to patch a fundamental tear in our cosmic fabric, to find a way for general relativity and quantum mechanics to coexist peacefully, or perhaps to reveal an entirely new layer of reality we haven't yet conceived. But black holes don't just break our physics at the singularity or through information loss, they also shatter our conventional notions of space and time. Remember those wild speculative ideas about black holes as gateways? The mathematics of general relativity, as mind-bending as it is, actually allows for the possibility of wormholes. Imagine a shortcut through space-time, a cosmic tunnel connecting two vastly distant points in the universe, or even two different universes altogether. Theoretically, if you could navigate the extreme gravitational gradients and avoid spaghettification, A wormhole might offer a path to another galaxy in an instant, or perhaps to a different epoch in time. Now, it's crucial to emphasize that stable, traversable wormholes are purely hypothetical. If they exist, they would likely require exotic matter with negative energy density to keep them open, something we haven't observed. But the mere theoretical possibility that black holes could be connected to such structures profoundly warps our understanding of cosmic connectivity. Could a black hole be an entrance to another universe, a baby universe, born from the collapse of a dying star? Or could they be a mechanism for cosmic recycling where matter that falls in emerges elsewhere, perhaps in a new form, or even in a different dimension? These aren't just science fiction fantasies. They are questions born from the very equations that describe black holes, questions that hint at a universe far stranger and more interconnected than we ever imagined. And if wormholes are possible, what about time travel? Ooh. The implications are staggering. If a wormhole could connect two different points in space-time, could it connect two different times? This is where the universe truly starts to break down, not just physically but causally. Imagine the paradoxes, going back in time to prevent your own birth, or altering a historical event. Our current understanding of causality, the idea that cause always precedes effect, would be utterly shattered. While most physicists believe that nature finds a way to prevent such paradoxes, perhaps through chronology protection conjectures, the fact that black holes, through their profound warping of space-time, even open the door to such theoretical possibilities is a testament to their reality-bending power. Yet, it's not all about destruction and paradoxes. Black holes, in their ferocious cosmic dance, also play a crucial, even creative role in shaping the universe. Far from being mere cosmic drains, supermassive black holes at the centers of galaxies act as powerful engines. As gas and dust spiral into their accretion disks, they heat up to millions of degrees, emitting torrents of X-rays and gamma rays, forming brilliant quasars and active galactic nuclei (SGN). These energetic outflows can influence star formation in their host galaxies, sometimes triggering new bursts of stars, other times suppressing them by blowing away the necessary gas. They are cosmic architects, not just destroyers, driving galactic evolution on a grand scale. They are the beating hearts of galaxies, powerful furnaces that regulate the growth and development of the colossal star cities we call home. And let's not forget our theoretical on primordial black holes. If they indeed exist in the vast numbers some theories suggest, they could solve one of the universe's most enduring mysteries: dark matter. This invisible substance, which makes up about 27% of the universe's mass, exerts gravitational influence but doesn't interact with light. If primordial black holes, formed in the earliest moments of the Big Bang, are abundant enough and fall within the right mass range, they could constitute a significant portion, or even all, of dark matter. This would be a monumental shift in our cosmic understanding, replacing an exotic, unknown particle with a familiar, albeit extreme astrophysical object. It would mean that black holes aren't just an anomaly. They are an intrinsic, fundamental component of the universe's very structure. So how do we begin to unravel these profound mysteries? How do we mend the broken parts of our cosmic understanding? The answer lies in relentless observation and groundbreaking theory. The era of gravitational wave astronomy, ushered in by observatories like LIGO and Virgo, is proving to be an unparalleled tool. The first direct detection of merging black holes in 2015 wasn't just a scientific triumph, it opened a completely new window to the universe. We can now hear the space-time ripples from these titanic collisions, providing direct evidence of black holes and allowing us to test general relativity in the most extreme gravitational environments imaginable. Future detectors like LISA, a space-based observatory, will be sensitive to lower-frequency gravitational waves, allowing us to detect the mergers of supermassive black holes and probe the very early universe. This new sense is giving us unprecedented insights into the dynamics of black holes, their populations, and their growth. And then there's the incredible feat of the Event Horizon Telescope, EHT, which gave us the first ever images of black hole shadows, first of M87 in 2010, and then of our own galaxy's central supermassive black hole, Sagittarius A, in 2022. These aren't direct images of the black hole itself, which is by definition invisible, but rather images of the superheated plasma swirling around its event horizon, creating a shadow against the bright background. These stunning visual confirmations allow us to directly measure the size and shape of these cosmic monsters, test Einstein's theory of gravity in their immediate vicinity, and gain crucial insights into the behavior of matter in their extreme gravitational fields. It's like finally seeing the dragons on that uncharted map, even if only in silhouette. Ultimately, the deepest solutions to the black hole paradoxes will likely come from a grand unified theory, a theory of quantum gravity, that seamlessly weaves together general relativity and quantum mechanics. Theories like string theory and loop quantum gravity are ambitious attempts to describe gravity at the quantum level, where the singularity might be replaced by a more nuanced quantum mechanical structure, and the information paradox could find a natural resolution. These are the frontiers of human knowledge, where the brightest minds are trying to rebuild the universe's rulebook, to create a single coherent narrative that explains everything from the smallest subatomic particles to the largest cosmic structures. The journey to truly understand black holes is far from over. It's a journey that demands new physics, new telescopes, and perhaps new ways of thinking about reality itself. It forces us to confront the very edge of what we know and what we can know. Black holes are not just cosmic oddities, they are ultimate cosmic laboratories pushing our understanding of space, time, matter, and information to their absolute breaking points. They are the universe's most profound paradoxes, and in unraveling their mysteries, we might just unravel the deepest secrets of existence itself. What new discoveries await us? What further paradoxes will black holes unveil? And how will our understanding of the universe be forever changed by these enigmatic objects? Join us next time on Dreamy Science as we continue to explore the mind-bending cosmos. If you're enjoying this journey through the universe's most extreme phenomena, please hit that like button and subscribe for more cosmic adventures. We'd love to hear your thoughts in the comments below. What do you think lies beyond the event horizon? Welcome back to Dreamy Science, where we continue our mind-bending journey into the heart of cosmic paradoxes. So far, we've explored how black holes form, how they warp space-time with their ferocious gravity, and how they stretch and distort everything we thought we knew about the universe. We've even touched upon the profound mysteries they harbour, like the elusive intermediate mass black holes and the tantalizing possibility of primordial black holes as dark matter candidates. But now, we're going to push past the event horizon of our understanding and confront the very core of why black holes don't just bend the universe's rules, they utterly shatter them, exposing the deepest cracks in our most fundamental theories. Remember that infinitely dense point at the heart of every black hole, the singularity? It's more than just a place where gravity wins. It's a place where our physics utterly breaks down. Imagine trying to use a map of New York City to navigate a black hole's interior. It's not just unhelpful, it's completely meaningless. All the beautiful equations of general relativity, which so elegantly describe gravity on cosmic scales, throw up their hands in despair when confronted with infinite density. They simply can't compute. This isn't just a minor inconvenience. It's a gaping wound in our understanding of reality. What is the singularity? Is it a point? Is it a tear in the fabric of space-time? A gateway? A cosmic error 404 message? We don't know. And that lack of knowledge, that fundamental blank space at the very centre of these cosmic monsters, is one of the most profound challenges in all of science. But the singularity is only one piece of the puzzle. The truly universe-breaking paradox emerges when we try to reconcile Einstein's majestic general relativity with the equally profound yet utterly different realm of quantum mechanics. These are the two pillars of modern physics, each incredibly successful in its own domain. General relativity describes the large-scale universe, gravity, planets, stars, and galaxies. Quantum mechanics describes the incredibly tiny world of atoms, particles, and fundamental forces. They are both incredibly accurate, but they speak different languages, and black holes are where their conversation devolves into outright shouting. The most famous example of this conflict, as we briefly touched upon, is the information paradox. This isn't just a theoretical squabble, it's a cosmic crisis. Here's why. In quantum mechanics, information is never truly lost. It can be scrambled, transformed, or hidden, but it always persists. Think of it like burning a book. The information in the book isn't gone, it's just encoded in the smoke, ash, and heat. In principle, if you had enough computing power, you could reconstruct the book from those remnants. It's a fundamental principle. Information is conserved. Now, enter the black hole. When something falls past the event horizon, general relativity tells us it's gone forever, swallowed by the singularity. And then we have Stephen Hawking's groundbreaking discovery of Hawking radiation. We learned that black holes aren't truly black. They slowly evaporate over unfathomably long timescales, emitting a faint glow of particles. But here's the kicker. This radiation, according to Hawking's original calculations, seems to be utterly random, carrying no information about what fell into the black hole. So you have a situation where a black hole forms, swallows a star or a planet, or even a copy of your favourite book, and then slowly evaporates into nothingness, leaving behind only random radiation. What happens to the information about that star, planet, or book? Did it truly vanish? If so, quantum mechanics is fundamentally wrong. If information is lost, it's like a magic trick where the rabbit truly disappears, not just from the hat, but from existence itself. This is not just unsettling, it's an existential threat to our understanding of the universe. It implies a fundamental flaw in one of our most successful theories, and that, my friends, is what we mean when we say black holes break the universe. So how do we fix this cosmic conundrum? Physicists are grappling with several mind-bending ideas, each more profound than the last. One of the most intriguing is the holographic principle. Imagine our universe isn't three-dimensional in the way we perceive it, but rather all the information describing it is encoded on a distant two-dimensional surface, much like a hologram. Just as a 3D image is projected from a 2D surface, our entire reality might be a projection from a lower dimensional boundary. Applied to black holes, this principle suggests that the information about everything that falls into a black hole isn't lost, but is instead painted onto the two-dimensional surface of the event horizon like a cosmic hard drive. When the black hole evaporates via Hawking radiation, this information is slowly released, albeit in a scrambled form, preserving the quantum mechanical principle of information conservation. It's an idea that truly flips our perception of reality on its head, suggesting that the universe might be a giant hologram. Another fascinating attempt to resolve the information paradox comes from string theory, one of the leading candidates for a unified theory of quantum gravity. String theory proposes that fundamental particles aren't point-like objects but tiny vibrating strings. In this framework, the singularity at the heart of a black hole might not be a singularity at all. Instead, it could be a fuzzball, a complex, fuzzy sphere of vibrating strings that fills the region inside the event horizon. This fuzzball would be incredibly dense, but it wouldn't have an infinite density, and crucially, it would have a defined structure, capable of holding and processing information. If black holes are fuzzballs, then information isn't lost. It's simply stored within the intricate vibrations of these strings, eventually escaping as the fuzzball evaporates. The idea of a black hole as a fuzzy, stringy object rather than an infinitely dense point is a radical departure, but it offers a potential path to reconciling gravity with quantum mechanics. These radical proposals, the holographic principle, fuzzballs, and the very concept of a unified quantum gravity are born out of the necessity to understand black holes. Black holes are not just cosmic destroyers, they are the ultimate laboratories, pushing our theories to their breaking point and forcing us to invent entirely new ways of thinking about reality. They are the crucibles where general relativity and quantum mechanics must finally merge, where space and time might cease to be fundamental, and where the very nature of information is put to the test. And what about those tantalizing theoretical possibilities we mentioned earlier, like wormholes? If general relativity allows for them, could quantum gravity stabilize them? Wormholes, those hypothetical shortcuts through space-time, could potentially connect distant parts of our universe, or even different universes altogether. Imagine stepping into a black hole, though not the destructive kind, mind you, and emerging in another galaxy, or even another dimension. If we ever develop a complete theory of quantum gravity, it might tell us whether such traversable wormholes are truly possible, or if they remain forever in the realm of science fiction. If they are real, then black holes aren't just breaking our universe. They're breaking it open into a multiverse of possibilities. This journey into the heart of black holes is, in essence, a journey into the fundamental nature of existence itself. Are space and time emergent properties rather than fundamental ones? Is information truly conserved, or can it be permanently erased? What is the true nature of reality at its most extreme limits? These aren't just abstract philosophical questions, they are questions that black holes, these ultimate cosmic paradoxes, force us to confront with rigorous physics. The quest for a theory of quantum gravity, whether it's string theory, loop quantum gravity, or something entirely new, is the holy grail of modern physics. It's the attempt to weave together the fabric of the universe, to understand gravity not just as a force, but as a manifestation of the quantum realm. And black holes are the ultimate test cases, the places where the threads of our understanding unravel, demanding a new, unified tapestry. So as we ponder these profound questions, remember that every new discovery about black holes, every theoretical leap, brings us closer to understanding not just these cosmic monsters, but the very essence of the universe we inhabit. They are the ultimate challenges, the ultimate mysteries, and perhaps the ultimate keys to unlocking the deepest secrets of reality. What do you think about the holographic principle or the idea of fuzzballs? Do these concepts make you question your perception of reality? Let us know in the comments below. Your thoughts and theories are always welcome here on Dreamy Science, as we continue to explore the universe's most mind-bending phenomena together. Don't forget to hit that like button and subscribe if you're enjoying this journey into the unknown. There's so much more to uncover, so many more paradoxes to explore, as we continue to ask, why do black holes break the universe? And more importantly, what will we learn about ourselves and our reality in the process of putting it back together? Welcome back, cosmic explorers, to Dreamy Science. We've journeyed through the mind-bending realities of black holes, those ultimate cosmic paradoxes that twist space, devour time, and challenge every assumption we hold about the universe. We've wrestled with the information paradox, peered into the theoretical maw of singularities, and even dared to dream of wormholes. But now we arrive at the precipice of the grandest challenge of all. How do we mend the broken fabric of our understanding? Because let's be honest, black holes don't just break our universe, they expose the cracks in our most fundamental theories. General relativity, Einstein's magnificent symphony of gravity and space-time, dances beautifully on the grand cosmic stage, describing the ballet of planets and the waltz of galaxies. But when it approaches the infinitely dense singularity within a black hole, it screams, it shatters, it tells us, I don't know. And then there's quantum mechanics, the whispering enigma of the subatomic world, revealing the quirky, probabilistic nature of reality at its smallest scales. It works wonders for atoms and particles, but it struggles profoundly when confronted with the colossal gravitational might of a black hole. We need something new, something revolutionary. We need a way to reconcile these two titans of physics, to forge a single coherent narrative that explains gravity not just as a smooth continuous warp in space-time, but as a quantum phenomenon, a discrete and energetic dance of fundamental particles. We need quantum gravity. Imagine, if you will, the universe as a vast, intricate tapestry. General relativity describes the sweeping patterns and grand designs of the tapestry itself, how it stretches, how it sags under the weight of stars. Quantum mechanics, on the other hand, describes the individual threads, the atoms and forces that weave together to form those patterns. But at the heart of a black hole, at the singularity, the tapestry unravels completely. The threads fray, the patterns distort beyond recognition. We need a theory that can describe both, the grand design and the individual threads simultaneously, especially when the fabric itself is under such unimaginable stress. This quest for quantum gravity is arguably the most profound challenge facing theoretical physics today. It's not just about explaining black holes, it's about understanding the very essence of existence, the true nature of space, time, matter, and energy. While we don't have a definitive answer yet, we have some incredibly compelling candidates, each offering a radical new vision of reality. Let's dive into two of the most prominent contenders, shall we? First up, we have string theory. Now, if you've heard of string theory before, you might associate it with extra dimensions or tiny vibrating strings, and you'd be absolutely right. At its heart, string theory posits that the fundamental building blocks of the universe aren't point-like particles, but incredibly tiny one-dimensional strings that vibrate at different frequencies. Think of them like the strings on a cosmic violin. Different vibrational patterns give rise to different particles. An electron is one vibration, a photon another, and yes, even the graviton, the hypothetical particle that mediates gravity, is another. What makes string theory so compelling in the context of black holes? Well, for one, it inherently includes gravity as one of its fundamental forces. Unlike other quantum theories that struggle to incorporate gravity, string theory emerges with it naturally. Crucially, it also offers a potential solution to the dreaded singularity. Instead of an infinitely dense point where physics breaks down, string theory suggests that at these extreme scales, the fundamental strings themselves would be the dominant feature. The singularity in this view might not be a point of infinite density, but rather a region where space-time warps so violently that it becomes a tangled, energetic mess of these fundamental strings. This is where the concept of fuzzballs, which we touched on previously, finds its theoretical home. A black hole from this perspective isn't a void with a singularity, but a quantum fuzzball of strings, potentially preserving the information that falls into it. No information loss, no paradox, just a radically different picture of reality. But string theory comes with its own set of challenges, most notably the requirement for extra spatial dimensions, often 6 or 7 of them, curled up so tightly that we can't perceive them. Imagine a garden hose from a distance. Looks like a one-dimensional line, but up close you see its two-dimensional surface. These extra dimensions are thought to be similarly compactified, but their existence is a bold prediction that remains experimentally unverified. Then there's loop quantum gravity, LQG, another powerful contender. Where string theory focuses on the fundamental constituents of matter, LQG focuses on the very fabric of space-time itself. Instead of seeing space-time as a smooth, continuous background, LQG proposes that it's actually made up of discrete, quantifiable loops or atoms of space. It's not a continuous sheet, but a finely woven, granular structure, much like a pixelated image on a screen. Imagine zooming in on space. According to general relativity, you just keep seeing smaller and smaller smooth space, but LQG says that eventually you'd hit a fundamental limit, a quantum of space, a tiny indivisible unit. This quantization of space is profound. It means that space and time aren't infinitely divisible. They have a fundamental, smallest possible scale, known as the Planck length and Planck time. How does this help with black holes? Just like string theory, LQG offers a way to avoid the singularity. If space itself is granular, then it's impossible to compress matter into an infinitely small point. Instead, at the extreme densities found within a black hole, LQG suggests that space-time might bounce or reach a maximum density, preventing the formation of a true singularity. This could even imply that black holes lead to other regions of space-time, perhaps even to other universes, a concept sometimes referred to as a white hole or a bounce into a new cosmic expansion. This is truly mind-bending stuff, isn't it? Both string theory and loop quantum gravity are attempting to answer the same fundamental question. What happens when gravity becomes so strong and space and time become so warped that quantum effects can no longer be ignored? They are trying to build a bridge between the vast, elegant cosmos of general relativity and the strange, probabilistic quantum world. And in doing so, they are utterly redefining our perception of reality. Think about it. If space isn't smooth but granular, if time isn't a continuous flow, but a series of discrete ticks, then our very intuition about the universe is fundamentally challenged. The empty space around you isn't truly empty. It's a vibrant, energetic foam of quantum loops or vibrating strings. The universe isn't just there. It's a dynamic, shimmering tapestry woven from these fundamental elements. And this leads us to perhaps the most speculative, yet utterly captivating implication of these extreme physics, the multiverse. If space-time can be stretched, warped, and even torn in the crucible of a black hole, if quantum gravity hints at dimensions beyond our perception, or granular structures that prevent true singularities, what does that mean for the existence of other universes? The idea of a multiverse isn't new, but black holes provide a fascinating, albeit theoretical, connection. Some interpretations of quantum gravity, particularly those involving a bounce at the singularity, suggest that what we call a black hole might actually be a gateway to another universe, or perhaps even the birth point of a new universe. Imagine our universe as just one bubble in a vast cosmic foam, and black holes are the tiny temporary connections between these bubbles. This is where the dreamy science truly embraces the dreamy. While purely theoretical, the possibility that black holes are not just cosmic devourers but cosmic architects, birthing new realities, is profoundly humbling and awe-inspiring. It transforms them from mere destroyers into fundamental engines of cosmic creation and connection. It suggests that the universe isn't just broken by black holes, but perhaps expanded and multiplied by them. So how do we test these incredible theories? How do we move from elegant mathematics and philosophical musings to concrete evidence? This is where black holes truly shine as ultimate cosmic laboratories. They are the only places in the universe where gravity is so extreme that quantum effects must become relevant. They are nature's particle accelerators, pushing physics to its absolute limits. Future observations from instruments like the Event Horizon Telescope, with even greater resolution, might reveal subtle deviations from general relativity's predictions around the event horizon, offering clues that could favour one quantum gravity theory over another. Gravitational wave detectors, becoming ever more sensitive, could potentially detect echoes or signatures from exotic objects that aren't quite black holes, but are predicted by quantum gravity, like fuzzball mergers or Planck stars, the hypothetical end state of a black hole in LQG. And beyond observations, the ongoing theoretical work is crucial. Physicists around the globe are tirelessly exploring the mathematical landscapes of string theory, loop quantum gravity, and other emerging ideas, seeking consistency, making predictions, and attempting to unify our fragmented understanding. The journey is long, complex, and often filled with intellectual dead ends, but the potential rewards are immeasurable. What does all this mean for us, for humanity, for our place in this vast, mysterious cosmos? It means that we are living in an era of unprecedented discovery, standing on the cusp of a revolution in physics that could redefine everything we thought we knew. Black holes, those terrifying yet beautiful cosmic monsters, are not just distant curiosities. They are the keys to unlocking the deepest secrets of reality. They force us to confront the limitations of our current understanding, to push the boundaries of the imagination, and to embrace the profound mystery that lies at the heart of the universe. The pursuit of quantum gravity is a testament to the human spirit of inquiry, our insatiable desire to understand, to explain, to connect the seemingly disparate pieces of the cosmic puzzle. It's a journey that takes us from the smallest vibrating string to the grandest multiverse, from the infinitesimally small Planck scale to the incomprehensibly vast cosmic web. And black holes, in their extreme reality-bending glory, are the signposts guiding us along this incredible path. If you've been enjoying this mind-expanding adventure into the depths of cosmic mystery, if you've found yourself pondering the granular nature of space or the possibility of other universes, then you're exactly where we want you to be. This is what Dreamy Science is all about, sparking that curiosity, fueling that wonder. Don't forget to hit that like button, share your thoughts in the comments below, and subscribe so you don't miss our next deep dive into the universe's most perplexing phenomena. The universe is far stranger, far more beautiful, and far more complex than we can possibly imagine. And black holes are here to remind us of that every single day. They break our universe, yes, but in doing so they also reveal its hidden, profound truths. Until next time, keep looking up, keep questioning, and keep dreaming big. Welcome back to Dreamy Science, my fellow cosmic explorers. If you've been with us on this mind-bending journey, you know we've plunged headfirst into the heart of black holes, those utterly extreme cosmic entities that don't just exist in our universe. They break it. They tear at the very fabric of our understanding, exposing the profound cracks between our two most successful yet tragically incompatible theories of reality, general relativity and quantum mechanics. Last time we touched upon the ultimate quest to mend these cosmic fractures with the unified theory of quantum gravity. We mentioned string theory and loop quantum gravity as two of the most promising candidates, each offering a radically different yet equally revolutionary vision of the universe. Today we're not just going to talk about these theories, we're going to dive into how they propose to fix the universe to resolve those infuriating paradoxes that keep physicists up at night: the infinitely dense singularity and the utterly baffling information paradox. Imagine, if you will, the singularity, that point of infinite density and zero volume where general relativity screams, "I give up," and all known laws of physics simply cease to apply. It's a mathematical abyss, a cosmic chasm that defies our intuition and our equations. And then there's the information paradox, the idea that information, once swallowed by a black hole, is lost forever, a direct violation of one of quantum mechanics' most sacred tenets. These aren't just minor quibbles, these are fundamental tears in the tapestry of reality as we understand it. But what if the universe isn't broken beyond repair? What if these theories offer a way to stitch it back together, perhaps even revealing a reality far stranger and more beautiful than we ever dared to imagine? Let's start with some string theory, a theoretical framework that at its heart suggests that the fundamental building blocks of our universe aren't point-like particles at all. Instead, everything, every electron, every photon, every quark, and even the graviton, the hypothetical particle that mediates gravity, is made of tiny, vibrating one-dimensional strings. And when I say tiny, I mean incredibly tiny, far smaller than anything we can currently observe. Think of it like a cosmic guitar. Different vibrational patterns of these strings give rise to different particles, each with its unique properties. One vibration might be an electron, another a photon, and another still, a graviton. Now, how does this incredibly elegant idea help us mend the universe, especially around a black hole? Well, string theory inherently includes gravity. It doesn't need to be bolted on as an afterthought. It's a natural consequence of these vibrating strings. And here's where it gets truly fascinating. String theory proposes that the singularity at the heart of a black hole doesn't actually exist in the way general relativity describes it. Instead, it's replaced by something called a fuzz ball. Picture this. Instead of a point of infinite density, a black hole from the perspective of string theory is a quantum fuzz of these vibrating strings. It's not empty space with a point at the center. It's a dense, entangled ball of quantum strings extending out to what we perceive as the event horizon. This fuzzball is not infinitely dense. It has a finite, albeit incredibly high density. And crucially, it is not a place where information is destroyed. Think of it like this. If you throw a book into a conventional black hole, general relativity says the information contained within that book, the arrangement of its atoms, the words on its pages, is utterly lost. But if you throw that same book into a fuzzball, the information isn't destroyed, It's absorbed and encoded into the incredibly complex quantum state of the fuzzball itself. The fuzzball becomes an intricate, holographic representation of everything that has ever fallen into it. It's like a super dense quantum hard drive storing every single bit of information. So when a fuzzball eventually evaporates via Hawking radiation, a process we discussed earlier, the information, though scrambled and incredibly hard to retrieve, isn't lost. It's subtly encoded in the outgoing radiation, preserving the sacred law of quantum mechanics. Information is never truly destroyed. This revolutionary idea, pioneered by physicists like Samir Mathur, offers a profound solution to both the singularity problem and the information paradox, transforming black holes from cosmic destroyers of information into complex quantum information processors. But string theory isn't the only game in town. Let's turn our attention to pole loop quantum gravity, LQG. Another incredibly ambitious attempt to unify quantum mechanics and general relativity. Where string theory posits that everything is made of strings, LQG takes a different approach, focusing on the very fabric of space-time itself. Imagine space-time not as a smooth, continuous sheet like a perfectly stretched rubber trampoline, but as something fundamentally granular, like a piece of finely woven cloth. LQG suggests that space-time is composed of discrete, indivisible atoms of space and time. These aren't tiny particles floating in space, they are space and time, quantized into fundamental loops. It's an utterly radical idea. Space and time aren't just a backdrop for events, they are dynamic quantum entities with a minimum possible size. There's a smallest unit of length, a smallest unit of area, a smallest unit of volume. Now, how does this granular space-time mend the universe at the heart of a black hole? If space itself has a minimum size, then infinite compression becomes impossible. The singularity, that point of zero volume and infinite density, simply cannot exist. LQG proposes that as matter collapses towards the center of a black hole, it can't compress indefinitely. Instead, it reaches a point of maximum density, a quantum limit where the fabric of space-time itself prevents further collapse. What happens then? This is where the concept of the Big Bounce comes into play. LQG suggests that instead of collapsing into a singularity, the matter might bounce back out, perhaps into another region of space-time, or even into a new universe entirely. This bounce isn't just theoretical for black holes, it also offers a compelling alternative to the Big Bang. Instead of our universe beginning from an infinitely dense singularity, the Big Bounce hypothesis suggests that our universe is merely the rebound of a previous collapsing universe. It's a cosmic cycle of death and rebirth, driven by the quantum nature of space-time itself. So for a black hole, LQG offers a singularity-free interior. The extreme curvature of space-time is still there. The event horizon is still the point of no return, but inside, instead of an infinite abyss, you might find a region of incredibly dense, but finite, quantum space-time. This prevents the ultimate breakdown of physics that GR predicts, and offers a potential pathway for information to not be utterly destroyed, even if its retrieval remains incredibly complex. The information might be preserved in the quantum geometry of space-time itself, or perhaps even bounce into another realm. Do you see the profound implications here? Both string theory and loop quantum gravity, in their own unique ways, offer solutions to the most challenging problems posed by black holes. They don't just tweak our understanding, they fundamentally redefine it. They propose a universe where the singularity is an illusion, where information is never truly lost, and where space and time themselves are not the smooth, continuous entities we perceive, but rather intricate quantum tapestries or vibrating symphonies of strings. These theories are our most ambitious attempts to build that elusive bridge between the macroscopic world of gravity and the microscopic world of quantum mechanics. They're trying to give us a theory of everything, a single coherent framework that can describe all forces and particles in the universe, from the smallest subatomic entities to the largest black holes and the entire cosmos itself. But, and this is a big but, both string theory and loop quantum gravity are still very much works in progress. They're incredibly elegant mathematically, offering tantalizing solutions, but they remain largely unproven. How do we test such extreme ideas? How do we peer into the quantum heart of a black hole or detect the subtle vibrations of fundamental strings? This is the grand challenge facing theoretical physics today. One avenue for testing these ideas lies in the very phenomena we've been discussing, black holes themselves. They're not just cosmic destroyers, they are our ultimate cosmic laboratories. Future generations of gravitational wave observatories, far more sensitive than LIGO and Virgo, might be able to detect subtle echoes or deviations from general relativity's predictions in the gravitational waves emitted by merging black holes. These tiny anomalies could be the telltale signs of a fuzzball structure or the granular nature of space-time. Imagine listening to the final death throes of two black holes and hearing the whisper of quantum gravity. The Event Horizon Telescope, which gave us that groundbreaking image of the M87 black hole shadow, is another crucial tool. As its resolution improves, and as we gather more data from different black holes, we might be able to detect subtle differences in the shape or behavior of the black hole's shadow that could hint at the quantum structure within. Perhaps the edge of the shadow isn't as perfectly sharp as GR predicts, but instead has a fuzzy quantum blur that reveals the underlying fuzzball or space-time granularity. And what about the early universe? If LQG's Big Bounce hypothesis is correct, we might find subtle signatures in the cosmic microwave background radiation, the afterglow of the Big Bang, that point to a previous cosmic era. These are incredibly subtle effects, requiring monumental technological advancements and painstaking analysis, but the potential rewards are immeasurable. Ultimately, whether it's string theory with its elegant fuzzballs, loop quantum gravity with its atomic space-time, or an entirely new theory yet to be conceived, the journey to unify gravity and quantum mechanics is a testament to human curiosity and our relentless pursuit of understanding. It challenges our deepest intuitions about reality, forcing us to confront the possibility that space, time, matter, and energy are far more interconnected and bizarre than we ever imagined. Black holes, those cosmic paradoxes that break our universe, are also the key to mending it. They are the extreme environments where our current theories fail, pushing us to develop new ones, to expand our minds, and to rethink everything we thought we knew. They are the ultimate teachers, revealing the profound mystery and intricate beauty woven into the very fabric of existence. So as we continue this incredible exploration, remember that the universe isn't just out there, it's within us, in every question we ask, every theory we propose, and every boundary we push. What do you think is the most mind-bending aspect of these quantum gravity theories? Let us know in the comments below. Your thoughts, your questions, and your own dreamy science explorations are what make this journey so incredibly rich and rewarding. Don't forget to like this video, subscribe to Dreamy Science, and hit that notification bell so you don't miss our next dive into the cosmic unknown. Until then, keep looking up, keep wondering, and keep dreaming big. Welcome back to Dreamy Science, where we don't just explore the cosmos, we dive headfirst into its most profound mysteries especially those that threaten to unravel our very understanding of reality. We've journeyed through the mind-bending landscapes of general relativity, navigated the quantum foam, and grappled with the cosmic paradoxes that black holes throw at us. We've seen how theories like string theory and loop quantum gravity offer tantalizing glimpses of a universe where singularities are smoothed out and information is never truly lost. But what does it really mean for our universe if one of these, or something entirely new, proves to be the answer to quantum gravity? This is where black holes truly earn their title as the ultimate cosmic laboratories, the ultimate proving grounds for the most extreme physics. Think about it. If you want to test the limits of a material, you don't just gently tap it. You subject it to immense pressure, extreme temperatures, and forces that would tear anything else apart. Black holes do precisely this to the very fabric of space-time, to matter, and to our most cherished physical laws. They are the universe's most ferocious stress test, revealing where our current theories buckle and break. Imagine, if you will, the Event Horizon Telescope giving us that groundbreaking image of M87's shadow, a testament to general relativity's stunning accuracy, even at the edge of oblivion. But what about inside that shadow? What about the conditions at the singularity, where general relativity itself screams error, divide by zero? This is where the theoretical heavyweights step in, offering alternative realities. If string theory is correct, then the singularity isn't an infinitely dense point at all. Instead, it's a fuzzball, a swirling, quantum-entangled mess of vibrating strings, stretching out to the event horizon itself. This isn't just a neat theoretical trick. It's a revolutionary reimagining of a black hole's interior. No longer an empty void behind the event horizon, but a complex holographic structure where information is stored, scrambled, and eventually, according to this theory, released as Hawking radiation. This would elegantly resolve the information paradox, a cosmic sigh of relief for quantum mechanics. The fuzzball isn't a simple featureless sphere, it's a dynamic, information-rich entity. And if we could somehow probe it, if we could find a way to detect the subtle imprints of these quantum strings, it would not only validate string theory, but also profoundly reshape our understanding of what nothingness truly means inside a black hole. Then there's loop quantum gravity, offering an equally radical vision. Instead of a singularity, LQG suggests that space-time itself is granular, made up of tiny, indivisible atoms of space and time. This means there's a minimum possible size, a quantum of space, which prevents anything from collapsing to infinite density. Instead of a singularity, matter reaches an incredibly high but finite density, and then what? The Big Bounce concept comes into play here. It suggests that instead of collapsing infinitely, the matter might bounce back, perhaps expanding into a new region of space-time, or even a new universe. This isn't just a solution to the singularity problem within black holes. It's an alternative to the Big Bang itself, proposing a cyclical universe where black holes might be gateways rather than dead ends. Think of it. The universe itself could be breathing, expanding and contracting with black holes as the cosmic valves. These aren't just abstract ideas discussed in ivory towers. They are our best attempts to describe a reality that is far stranger and more complex than we ever imagined. And black holes, these cosmic behemoths, are the only places in the universe where we can truly put these theories to the test, even if indirectly. We can't send a probe into a black hole and expect it to send back a postcard, at least not yet, but we can look for subtle observational cues. Are there gravitational wave signatures that deviate from general relativity's predictions? hinting at a fuzzball's surface or a bounce's echo. Could future, even more sensitive gravitational wave detectors, like the proposed space-based LISA mission, pick up such whispers from the cosmos? This is the grand challenge, the ultimate detective story played out on a cosmic scale. But the implications of solving quantum gravity extend far beyond just understanding black holes. A theory of everything, a unified framework that seamlessly marries general relativity with quantum mechanics, would be the holy grail of physics. It would allow us to describe the universe from the smallest subatomic particles to the largest cosmic structures, from the first moments of the Big Bang to the final fate of the universe. It would unlock secrets that we can currently only dream of. Imagine being able to truly understand the origin of the universe. The Big Bang, as we currently understand it, starts from a singularity, a point of infinite density and temperature, where our equations again break down. But if LQG's Big Bounce is correct, the Big Bang wasn't a beginning ex nihilo, but a rebound from a previous cosmic collapse. This would fundamentally alter our understanding of cosmic history, suggesting an eternal cyclical universe, or perhaps even a multiverse where new universes are constantly being born. And what about the very nature of space-time itself? If space-time is granular, as LQG suggests, then it's not the smooth, continuous fabric Einstein described. It's more like a pixelated image with a fundamental resolution limit. This would mean that at incredibly small scales, reality itself might be grainy, a concept that is truly mind-bending. It challenges our intuitive understanding of continuity and smoothness, forcing us to confront a universe that is far more digital than analog at its most fundamental level. This leads us to one of the most profound and unsettling concepts to emerge from the study of black holes and quantum gravity, the holographic principle. We mentioned it briefly before, but let's really lean into it now because it utterly breaks our conventional perception of reality. The holographic principle, inspired by black hole thermodynamics and string theory, suggests that all the information contained within a three-dimensional volume of space can actually be encoded on a two-dimensional surface enclosing that volume, much like a hologram, where a 3D image is projected from a 2D surface. Think about that for a moment. Imagine our entire three-dimensional universe, with all its stars, galaxies, planets, and even us, is merely a projection, a cosmic hologram, encoded on a distant two-dimensional boundary. It's like watching a 3D movie, but the actual information creating that experience is stored on a flat screen. This isn't just a quirky idea, it's a powerful mathematical concept that emerges from attempts to reconcile gravity and quantum mechanics. If true, it means our perceived reality, our very sense of depth and three-dimensionality, might be an illusion. We could be living in a cosmic projection, a grand cosmic illusion. How's that for breaking the universe? The holographic principle offers a potential resolution to the information paradox by suggesting that information isn't lost within a black hole, but is instead flattened and stored on its event horizon, much like data on a cosmic hard drive. When a black hole evaporates via Hawking radiation, that information is slowly radiated back out, albeit in a scrambled form. It's a breathtaking idea that suggests a fundamental connection between information, gravity, and the very structure of space-time. It challenges the very notion of what is real and what is fundamental about our universe. Are we characters in a grand cosmic simulation, or is reality simply far more subtle and interconnected than our everyday intuition allows? The pursuit of quantum gravity is not just about understanding black holes. It's about understanding the very essence of existence. It's about revealing the operating system of the cosmos and the journey is far from over. We're building new observatories, pushing the limits of particle accelerators, and devising ever more sophisticated theoretical models. We're looking for subtle anomalies in the cosmic microwave background, searching for evidence of primordial black holes that could be dark matter, and listening for the faintest echoes of gravitational waves that could reveal the quantum nature of space-time. The challenges are immense, the concepts are mind-bending, and the answers are elusive. But that, my friends, is the beauty of science. It's a relentless quest for truth, a journey into the unknown that constantly pushes the boundaries of human knowledge and redefines our perception of reality. Black holes, these cosmic monsters, are not just destructive forces, they are the universe's most profound teachers, forcing us to confront the limits of our understanding and inspiring us to dream of a universe that is far more wondrous and interconnected than we ever dared to imagine. So as we contemplate these ultimate cosmic laboratories, these incredible paradoxes, remember that every question we ask, every theory we propose, every observation we make brings us one step closer to mending the broken fabric of our universe. And who knows what incredible reality-shattering truths we might uncover next. Stay curious, keep exploring, and never stop dreaming about the science that shapes our universe. If you're enjoying this journey into the extreme, hit that like button, subscribe for more cosmic adventures, and let us know in the comments what mind-bending concept about black holes or the universe keeps you up at night. Welcome back to Dreamy Science, where we don't just explore the cosmos, we reimagine it. Last time we dove headfirst into the dizzying realm of quantum gravity, those valiant attempts to mend the cosmic rift between Einstein's elegant general relativity and the bewildering world of quantum mechanics. We saw how string theory offered us fuzzballs instead of singularities, quantum entangled structures that might just preserve information, and how loop quantum gravity proposed a granular space-time, preventing infinite compression and perhaps even hinting at a big bounce. But these aren't just fixes for black holes, my friends. Oh no, these are radical reality-bending propositions that force us to confront questions far more profound than just what happens inside a black hole. They challenge the very fabric of our existence, the nature of reality itself. Are you ready to have your mind truly stretched? Because today, we're going to pull back the curtain on some of the most audacious ideas born from our quest to understand black holes, the holographic principle, the deeper implications of wormholes, and the tantalizing, terrifying concept of the multiverse. Let's start with the one that might make you question everything you thought was solid and real, the holographic principle. Imagine for a moment that everything you see, feel, and experience, this entire three-dimensional universe, with all its stars, galaxies, and even you, my curious friend, is nothing more than a projection, a cosmic hologram, if you will, emanating from a two-dimensional surface at the very edge of our universe. Sounds like science fiction, right? Well, it's a profound idea that emerged directly from our attempts to understand black holes. Think back to the Bekenstein-Hawking entropy, that groundbreaking realization that black holes have an entropy proportional to their surface area, not their volume. For any other three-dimensional object, the amount of information it can hold scales with its volume. But for a black hole, it's the boundary, the event horizon, that holds the key. This was a massive clue, a cosmic whisper suggesting that perhaps the fundamental degrees of freedom, the bits of information that make up reality, reside not in the volume of space, but on its boundary. It's like a security chip on your credit card. All the complex information isn't inside the chip's volume, but encoded on its flat surface. This isn't just a quirky observation, it's a deep mathematical insight. The most robust realization of this idea comes from something called the Isar-ADS-CFT correspondence, or anti-de Sitter conformal field theory correspondence. Don't worry about the jargon. What it essentially tells us is that a theory of gravity in a specific kind of curved 3D spacetime, anti-de Sitter space, is mathematically equivalent to a quantum field theory without gravity living on its 2D boundary. It's like having two completely different descriptions of the same reality, one in 3D with gravity and one in 2D without it. While anti-de Sitter space isn't exactly our universe, this correspondence provides a powerful working model for the holographic principle. It shows us that such a thing is mathematically possible. So if our universe were a hologram, what would that mean? It would mean that the stuff we perceive as solid, as existing in 3 dimensions, is fundamentally an emergent property. The true fundamental reality might be a simpler 2-dimensional quantum description. Our perceived 3D reality, with all its depth and volume, would be a projection, much like a 3D image projected from a 2D piece of film. It's a concept so profound, so challenging to our everyday intuition, that it literally breaks our understanding of what real is. Is your hand truly 3-dimensional, or is it an incredibly detailed, convincing illusion? Black holes, these ultimate cosmic paradoxes, are the very reason we even ask such mind-bending questions. Now, let's circle back to those cosmic shortcuts we touched on before. Wormholes. If space-time itself can be warped and torn by the ferocious gravity of black holes, then perhaps it can also be stitched together in impossible ways. Wormholes, those hypothetical tunnels through space-time, are a direct consequence of general relativity, much like black holes themselves. They offer a tantalizing yet deeply problematic solution to the vast distances of the cosmos. Imagine traversing light years in an instant, not by travelling through space, but by travelling around it through a cosmic shortcut. The initial wormhole solutions, like the Einstein-Rosen bridge, were quickly found to be non-traversable. They pinch off faster than anything could cross them. They were like bridges that collapsed the moment you stepped onto them. But the dream of traversable wormholes persists, leading physicists to explore the need for exotic matter. This isn't just any matter. We're talking about matter with negative energy density, something that would exert a repulsive gravitational force, propping open the wormhole long enough for something to pass through. Such matter has never been observed, and its existence pushes the boundaries of known physics, but quantum mechanics does allow for fleeting instances of negative energy in very specific microscopic scenarios. Could it be harnessed on a cosmic scale? If traversable wormholes do exist, the implications are utterly staggering. Interstellar travel would be revolutionized, making distant galaxies potentially accessible. But the real mind-bender is the possibility of time travel. If you could travel through a wormhole that had one end moved at relativistic speeds, time dilation would mean that the two mouths of the wormhole would experience time differently. Stepping through could send you into the past or future. This immediately plunges us into the realm of paradoxes, the infamous grandparent paradox, for example, where you could theoretically prevent your own birth. These paradoxes are so fundamental that many physicists believe they point to a fundamental prohibition against time travel, perhaps through a chronology protection conjecture that prevents such causal violations. But the fact that black holes, through their influence on space-time, even suggest such possibilities, is a testament to their profound reality-breaking nature. They are cosmic laboratories for the impossible. And finally, let's talk about the ultimate expansion of reality, the grandest hypothesis of all, the multiverse. If black holes are so extreme, so fundamental to the structure of space-time, could they be more than just destroyers? Could they be creators, or perhaps gateways? The idea of a multiverse isn't a single concept, but a family of theories, each with its own compelling, if unprovable, arguments. Black holes play a starring role in several of them. In some interpretations of string theory, our universe isn't the only one. Instead, it's just one brain, a higher dimensional membrane, floating in a vast, higher dimensional bulk. Other brains, other universes, could exist parallel to ours, perhaps only a Planck length away, interacting with us only through gravity. Black holes, in this context, might be places where our brain interacts with others, perhaps even pulling matter and energy from them. Then there's the eternal inflation model, where the universe isn't just expanding, but different regions of space are inflating at different rates, constantly spawning new bubble universes. Our observable universe would be just one such bubble. Black holes, in this scenario, could be the remnants of these inflationary processes, or perhaps even the seeds for new inflationary bubbles in other regions of space-time. And let's not forget the big bounce concept from loop quantum gravity. If the singularity inside a black hole isn't a point of infinite density, but a point of maximum finite density, what happens next? Instead of collapsing into nothingness, it might bounce back, expanding into a new universe. Every black hole in our universe could potentially be a seed for a new baby universe, growing on the other side of its event horizon. This turns black holes from mere devourers into cosmic nurseries, constantly giving birth to new realities. Even the many worlds interpretation of quantum mechanics, which posits that every quantum measurement causes the universe to split into multiple parallel realities, can be seen as a form of multiverse. While not directly tied to black holes in their formation, the quantum nature of black holes, especially the information paradox, touches on the very core of quantum reality and its many possibilities. The multiverse concept is perhaps the most audacious idea in modern physics, and it's one that black holes push us towards. It suggests that our universe, with its specific laws and constants, might just be one of an infinite number of universes, each with its own unique properties. This could potentially explain the fine-tuning problem, why our universe seems perfectly calibrated for life. If there are infinite universes, then it's not surprising that at least one of them would have the right conditions for us to exist and ponder these very questions. But here's the rub, the ultimate challenge. How do we test any of this? How do we verify if our reality is a hologram, if wormholes are traversable, or if we're merely one universe in an infinite cosmic tapestry? For now, these ideas remain at the cutting edge of theoretical physics, born from the profound challenges posed by black holes. They are elegant, mathematically consistent, and incredibly compelling, but they often lie beyond our current observational capabilities. This is why black holes are so much more than just cosmic vacuum cleaners. They are the ultimate cosmic laboratories, forcing us to rethink every fundamental assumption we have about space, time, matter, and even consciousness. They break our universe, yes, but in doing so they also break open our minds, revealing vistas of possibility we could never have imagined. They are the crucibles where the laws of physics are pushed to their absolute limits, demanding a unified theory that can explain everything from the smallest quantum fluctuation to the largest cosmic structure. The journey to truly understand black holes is far from over. We are just beginning to scratch the surface of these enigmatic objects, and with every new discovery, every new theoretical leap, we find ourselves confronting deeper, more profound questions about the nature of reality itself. And that, my friends, is the most exciting adventure of all. If you've been enjoying this mind-bending journey through the cosmos, Make sure to hit that like button and subscribe to Dreamy Science for more explorations into the universe's greatest mysteries. We'll continue our quest next time as we delve even deeper into the ultimate questions black holes pose for the future of physics and humanity. Until then, keep dreaming big and keep looking up.